Hi everyone, thank you so much for coming. I'm Joe, I work at Poolside as a founding engineer, and this is Aiding the CUDA compiler for Fun and Profit. So just to give you a high-level idea about what this talk is about, we're essentially going to go into some situations where the CUDA compiler doesn't generate code that is perhaps optimal, and ways that you can coax the compiler into making code that's better for you. So just to give you some background on myself, so I'm a founding engineer at Poolside. I work on sort of low-level performance topics, I guess. Before I worked at this, I actually was doing a PhD in cryptography, so very, very different to AI. And the thing that you should know about me is I love low-level and arcane hardware facts. So if you come up to me and say, hey, Joe, did you know that this Core 2 Duo from 15 years ago had this property? I'm probably going to love it. But with all of that said, I just want to motivate this presentation slightly by telling you a story. So when I was doing cryptography, I used to teach programming labs. And occasionally you would get some very precocious student that would come up to you and say something like this: Joe, why don't we just write assembler? And to them, of course, it was kind of obvious that you wouldn't necessarily want to write in a high-level language because, it's not performant, right? And if you're so genuinely gifted at computer programming, maybe you can get away with writing an assembler. And of course, we all know that there are issues with high-level languages. You can't necessarily express your intent very clearly, but certainly there are reasons as to why you would want to use low-level languages in situations where you can, right? And I think in particular in high-performance settings, you really want to be able to do this. You want to be able to coax as much as you can out of your hardware. And sometimes assembly is the only way to do that. But on the other hand, we have so much code, there are so many lovely features. Really what we want is we want to be able to express our intent very clearly in a high-level language and get the compiler to do nice things. And so that's what the context of this talk is. We're going to try to figure out how we can get as much as possible out of our CUDA hardware. So before I dive in, I just want to give you a little bit of context. So a CUDA GPU is inherently a very parallel piece of hardware. Most of us, when we're writing software on a regular basis, we're thinking more about single-threaded applications. When we write our C code, it's very much in a single-threaded mindset to begin with. But CUDA GPUs are very much not like that. Instead, when you're writing code for a CUDA GPU, you're really thinking about your smallest unit of operation, which is much like with CPUs as a thread. The difference is that when you're writing your code for your thread, in the back of your mind, you're thinking about how that will parallelize over many, many, many other threads that will also run. And it turns out that these threads are, like in many things, are logically grouped into these things called blocks. So you can imagine maybe you're writing a program that says sort some numbers. And actually what you want to be able to do is you say, actually, I want to have, say, 10 blocks, or 10 threads in my block, or 11 threads in my block, or so on. And this is a nice user configurable parameter that enables you to scale how parallel your program is. Now, these blocks have a useful property, which is that threads that are in the same block can communicate with each other. So, for example, in the sorting setting, perhaps what you have is some threads that are sorting a small part of a sublist, and you want them to be able to communicate with each other. And that's when you would use a block. On the other hand, if you've got a really large problem, maybe you want to have many of these blocks. And these are grouped into things called grids. Now, unlike with blocks, threads that are across the same grid cannot communicate without going back to global system memory. Whereas with threads that are in the same block, you have some other things that are available. In context, this maps to the hardware in a very particular way. So although you can make your blocks as large as you want within reason, when your threads actually execute on the hardware, they are scheduled in groups of 32 threads. And this grouping of these threads is called a warp. So every warp is comprised of exactly 32 threads. And like I've said, when your code actually runs, the hardware will schedule this in blocks of 32, which is something that, as you'll see when we go through these slides, really helps you get as much as you can out of the hardware. Notably, warps actually execute on these things called streaming multiprocessors, or SMs. And you can think of these as like CPU cores, right? So you have your various operations that your core can do, various hardware resources, and those are shared across your SM. It's a physical hardware unit. And of course, on more modern GPUs, you have multiple of these SMs to make up the entire thing. So the latest and greatest hardware will typically have many hundreds of these SMs. And it's important to point out that when you're writing CUDA code, you cannot explicitly necessarily map your software constraints to the hardware. There's no way of saying, do this in this particular context, right? You've really got to be mindful of what the underlying hardware is whilst you're writing your CUDA C. Now, of course, as with any high-level language, you have to pass it through a compiler. The compiler will generate some assembly code. And in the context of CUDA, this is what it typically looks like. So this is called PTX assembler. This is the very high-level assembly language that CUDA provides. And it's worth pointing out that this assembler is supported across GPU generations. So if you wanted to write some code in PTX, if you wanted to drop into your editor and do ASM volatile and write some code, this is what you would write. And it's normally stable and compatible across different machine architectures. Now, of course, this depends. Obviously, new PTX instructions are introduced with new generations, but primarily speaking, most of the instructions stay the same. However, important thing to note is that PTX is not actually what runs on your GPU. In practice, what runs on your GPU is this thing called SAS. And the important thing to remember about SAS is that it is not stable. So SAS changes with every hardware generation, or may change with every hardware generation. And you can't very easily write it directly. So if you're writing your ASM volatile statements and you put some SAS in there, I don't think there's any guarantee that it will get passed through to your underlying application in a meaningful sense. It's normally just discarded by the assembler. So it's worth keeping this in mind, that even if you look at your PTX, it's not necessarily what actually is going to be executed on the hardware. SAS is actually what gets executed. And we'll see some examples later on as to where this difference actually matters. So now we've gone through all of that, we're going to go into our first tip. So although I already mentioned that when you're writing CUDA, you tend to write it from the perspective of a single thread, I really want to encourage you not to do this. I really want to encourage you to write code that is focused on the notion of a warp, or at the very least is focused on how your code will actually parallelize on the underlying hardware. So I want to give you an example for this. So this code looks probably quite daunting to begin with, but I'll walk you through it. When you have your CUDA code that executes, as already mentioned, it runs in groups of 32 threads. And it's important to point out that each of these threads have their own limited hardware resources. They all have access to some number of registers. They will have access to some local computation resources, but they're really quite limited. And actually, if your threads take up too much memory or require too many registers, it actually can prevent more work from being scheduled later, because you've only got a limited number of hardware resources. Now, this is a pain if you, for example, have some constant that is actually going to be the same across all 32 threads, right? Maybe maybe you have something where actually you want to have some shared result across all of your threads that are running in your particular warp. Now, conveniently, more recent CUDA generations have introduced this thing called a uniform register. And the way I want you to think about this is it's kind of a unsimdifying your CUDA code. So normally when you run CUDA, it's very parallel. You've got multiple threads doing things at once. But there is capability for the compiler to say, actually, I just want to treat this as a scalar operation that's going to be shared everywhere. And these uniform registers are really useful. These uniform operations are really useful because they enable further hardware optimizations, further compiler optimizations down the line. So just to give you an example of this, so this particular piece of code that's on this slide is designed to mark a particular variable, so this thing value that's been passed in, as the same across all of the threads in your warp. Now this is, obviously if you had something like an integer, maybe this doesn't matter so much, but actually if you have a CUDA program that when it begins increments a pointer, say, depending on your thread ID, it can actually be very useful to tell the compiler, oh, by the way, this is the same across all of the threads in the warp, to get that sort of register sharing property that I mentioned earlier on. Now, obviously this is quite a lot of code and I don't want to alarm you. When you run your PTX, so when you compile your program, you end up with something that looks like this. So this is your PTX assembly. It's gone through the the NVIDIA compiler, and it's produced this as your output. This is just the previous slide's code, but instantiated with an integer pointer. And you can see here that it generates something in PTX, right? You can see that there's some movements, there's some shuffling, there's some things going on. But what I want to point out now is that if you actually look at the SAS, you'll see that there's nothing. And this is, I really want to highlight this as a point. This just goes to show that you can't necessarily judge what's going to happen on your, when you employ these optimizations just by looking at the PTX. You really need to look at the SAS that's under the hood. You really need to check and actually see what's happened. Because if you had just looked at the PTX on the previous slide, you might think, oh, actually, this so-called optimization is actually costing me something. But in practice, when you look at it here, you'll see that actually there's no impact at all. It doesn't even impact your runtime in any way. And the advantage of this is that you can see that it truly is just a compiler optimization. It really just helps the compiler to generate better code rather than one of these things that sort of, you trade something here and then you gain something there. It really is about just getting as much as you can out of this particular thing. So I'm now going to give you another example of this. So I mentioned earlier on that threads in the same warp can communicate. And this actually has some advantages when it comes to doing certain operations. So one of the canonical examples as to where you want to communicate amongst threads that are in the same warp is if you're doing some reduction, right? So if you, let's say you want to sum all of the numbers in some small part of a list, or maybe you, as in this case, you want to compute the minimum of some values that are held by all of the threads. Now, this code here just shows you how to do this with regards to when you're using these shuffles. So just to talk you through the code slightly, this __ shuffle down sync here on the fourth line, what this does is it says, I am at thread, let's say I, and I want to read from the thread whose index is I plus offset. So if we walk through this loop slightly, you can see that to begin with, thread 0 will read from thread 16, thread 1 will read from thread 17, and so on. And it's important to note that if your thread ID is, say, 31, and offset is going to push you outside of that range, nothing happens. It's just a no-op. And then you can see here that just beneath that, we have this reduction. So we're saying, oh, if this is our new minimum, then I'm going to assign it. And when we go around the loop each time, we sort of shrink our offset down. So in the second iteration, thread 0 will read from thread 8, thread 2 will read from thread 9, and so on. And this thing happens. And eventually you end up with your thread index 0 having the minimum value. Now, you can, if you want to share this across all of the rest of the threads, do another shuffle afterwards. But this really gives you some nice performance speedups in practice. The other ways that you could do this is you could write back to global memory and do a minimum that way, but that's really expensive, or use some other communication methods. So for example, as opposed to just communicating over the threads in the warp, you can do it across the entire block, but that's far more expensive. Doing it this way really only takes a few cycles. And that's, in some situations, that can be really, really useful. My next tip, which is related to the previous tip, is where you can, you really want to use registers explicitly. You want to, as much as you can, focus on keeping things as close to the threads that you've got as you can, rather than going back to, say, main memory or so on. So just to quantify why this matters, in the previous example that I just gave with warp shuffles, you normally save about 20% all in once you've done this over using, say, atomics or other operations. But just in the broad scheme of things, actually you could get a lot more out of this. So if you're accessing a cache, for example, normally that takes you, say, 5 cycles, as opposed to 1 for just a register. But if you look at this bottom line here with global memory, that is substantially higher, right? It's 100 times larger than accessing the cache or shared memory, and it's 500 times larger than just accessing registers. So although the speed up from in practice might actually be somewhat different, it's still well worth designing your algorithms that in a way that considers this. It's something to point out that's really important is the compiler will never make this optimization for you. So the CUDA compiler will never look at your code and go, oh, you're using a shared memory there, for example. I'm going to instead use registers. It will never make that sort of optimization for you. It can do with global memory to register memory accesses, certainly, but it's very easy to fall afoul of certain coherency rules that will mean that actually the compiler is less likely to do that particular transformation for you. This is really one of those things where if you want to get that performance out, you have to do it by hand. So I just want to give another example of some inefficient ways to use memory in your CUDA kernel. So this is a very straightforward program that assumes that you've got a block with 1,024 threads that are running, and those threads are going to add all of the values that are in this pointer in together and store them in out. So this top line here creates what's called shared memory. Now, shared memory, I've sort of already mentioned it, is memory that is accessible by all of the threads that are in your block. So whilst you have this, and it's a very useful facility to have, accessing it is, as I said, is 5 times slower than accessing a register normally. And also you only have a limited amount of it because it's a dedicated hardware resource. And what this means is that you have to be very, very careful when you're using it to make sure that you're getting good amounts of performance out of it. So you'll see here, for example, there's these __ sync threads. What that means is that we're trying to take our operations, because these threads are all accessing a shared resource, and we're synchronizing them. And what this means is that actually you end up with certain threads that are faster, waiting for other threads to finish their work to make sure that everything is coherent. So in addition to this overhead that you've got, you're also paying a lot of extra performance cost in terms of just synchronizing stuff. By contrast, obviously this is quite a simple example, but you could just use a singular register per thread to do this. And that gives you this advantage of actually not needing to do the synchronization, not needing to dedicate any hardware resources other than just registers to this. It makes your life much better. I think in practice, I've seen around about a 22-23% speed up from this in practice. Obviously, it depends on your task and whether this is a bottleneck or not, but it can really give you a fairly good speed up, even in practical applications, when you make this transition. And just as the very last thing, I want to highlight that it's very, very easy to write CUDA code that is full of unfriendly access patterns. And so by this, I mean, for people who have written high performance C code, you're probably aware that on x86, a cache line is 64 bytes. In CUDA, it's slightly different. So accesses in CUDA typically come in 3 varieties. They come in a 32-byte load, a 64-byte load, and a 128-byte load. And if you really, really want to get optimal performance out of your CUDA kernels, you have to ensure that the memory accesses that you're doing are contiguous. So by this, I mean, let's say you've got an array of 1,024 elements. You really want to make sure that you're accessing that in contiguous chunks. And in particular, you need to make sure that the accesses are contiguous across the threads in your warp. So if you have your 32 threads, thread 0, thread 1, thread 2, all of those threads, they need to access the same contiguous chunk of memory. Now, you can play fast and loose with this somewhat. You don't need to access them quite so strictly, but the chunk that you're loading does need to be contiguous. Ideally, you would also make sure that the access you're doing is aligned, so that you're accessing a pointer that has the correct alignment, because then if the compiler can guarantee that, it will generate these nice 128-byte loads. It will make it so that it doesn't have to break them down so much. So I just want to give an example of a very poor access pattern, which is this. Now, this is the same summation example as before, but what's different here is that each thread now has an offset. So thread 0 will start at 0, and then it will read in 1, in 2, in 3, and so on. Whereas thread 1 will start at 1024, 1025, and so on. Now, functionally, this is the same as the previous kernel that I showed you, but the difference here is that your threads are not accessing memory sequentially, right? So each thread certainly has a sequential access, but the threads in your warp are not accessing memory sequentially. And what this means is that the hardware will actually not take the best advantage of the memory bandwidth that it's got, and it will spend a lot of time just spinning its wheels trying to load from memory when it could have been so much faster. So just to show you what the underlying SAS looks like, you can see here that the compiler has generated a series of load instructions. And you can see that actually the gap between the loads is as you would expect. It's 4 bytes as the offset. And it's worth pointing out that actually it's very, very similar to the SAS for the CUDA access pattern. Right here you can see that the access pattern is 1024 offset in the summation. And the reason why I mention this is because it's important to realize that although looking at your SAS is good from a performance perspective, these actually look rather similar. Right? The code that's on this slide looks very similar to the code that's on the previous slide. The main difference is that actually here, first of all, you can see that the offsets are rather strict. And second of all, if you were to profile this code, you would see that there is a substantial difference. You would see that this slide's code runs much, much faster from a memory access perspective. And so the moral of this story, I guess, is even if you can coax your CUDA compiler to generate nice code for you, it's still worth looking and profiling what's actually going on, because there you'll find out much more about why your application is actually slow. And with that, I would like to say thank you very much for listening to my presentation, and I'm here to answer any questions.